Captain Evil. Told you wouldn't make it. Dear Tim and Logan, can you help me on using similar figures? Thanks, Chase Dixon. Sure thing, Chase. In everyday conversation, the word similar is just another way of describing things that are alike. But in math, it has a more specific meaning. Figures are geometrically similar if they have the same shape, but not necessarily the same size. Nope, it doesn't mean that all triangles are similar. Triangles can have very different shapes. Take the triangle on Captain Evil's chest. His triangle of evil. Sorry. Oh, okay, as you can see, it's an equilateral triangle, which means it has 3 sides of equal length and 3 60-degree angles. So now, check out this wooden block, which is also triangular. This is a scalene triangle with sides of different lengths and 3 different angles. Geometrically similar triangles have to have corresponding angles that are congruent or equal. These don't. And they would have to have corresponding sides that are all proportional in length. And that means that the relative lengths of the sides would have to be the same. Our equilateral triangle has sides of lengths 2 centimeters, 2 centimeters, and 2 centimeters. Since they're all the same, we can reduce that ratio to 1 to 1 to 1. The scalene triangle has sides of 6 centimeters, 8 centimeters, and 10 centimeters. We can reduce those numbers by dividing by 2 to make the relative sizes 3, 4, and 5. The sides are obviously not in the same proportion, and the angles are all different. So these triangles are not similar. Good idea. Let's compare Captain Evil's triangle with the triangle formed by the ground and our swing set's legs. The angles of this big triangle are all 60 degrees, just like the triangle of evil. And since the sides are all the same length, they form the same ratio with the corresponding sides of the smaller triangle. So they're officially similar. Right, even though the swing set triangle is much bigger than the triangle of evil, the corresponding sides have the same proportions. If we want to find out the size difference between the 2 triangles, we can use something called scale factor. To find the scale factor between 2 similar geometric shapes, you just simplify the ratio between any 2 corresponding measurements, not including angles. Let's use 2 sides from our triangles. The ratio is 4 meters to 2 centimeters. The big triangle is 200 times bigger than the small one. By the way, this applies to all kinds of shapes, not just triangles. Well, all squares are similar by definition, since they all have 4 equal sides and 4 90-degree angles. The same goes with circles. You can read more about that in our features. But other shapes you do have to measure out. Sure, there's plenty of things you can do with similar figures. One is called indirect measurement. That's a way to measure things that are way too big to measure directly, like how tall that tree is. See how the tree casts a shadow to make a triangle? Well, we can use a meter stick to create a similar shadow and triangle. We already know the length of the meter stick, 1 meter, and we can measure the length of both shadow lines on the ground. Now we make a ratio for the lengths we know and solve for x. The tree is 8 meters tall. Which is exactly how far Agent Awesome can toss your puny Captain Evil if he's dumb enough to... Hey!
Okay, so we're going to be talking about similar figures. As we've just seen in the Brain Pop movie, figures that have the same shape but are not necessarily the same size can still be similar figures. So one is bigger or smaller than the other, but they have some similarities. They're similar. For example, the sides of similar figures that match are called corresponding sides. So when we're looking at these two triangles here, we got the longest side of the large triangle, ST, and the longest side of this triangle, which will be YZ, are corresponding. They're the same side on each triangle. They match up, the longest side to the longest side. Then obviously we have the shortest and the shortest match up, and the medium and the medium. So these are the corresponding sides. This green one's corresponding to that one, blue to blue, red to red. These are our corresponding sides. And then we also have corresponding angles. And the corresponding angles of similar figures have the same measurement. They match. So this angle here is 118, and so is this one. 26 and 26, 36 and 36. So our sides and our angles correspond, and the angles actually have the same measurement in a corresponding figure. When we're looking at these two triangles, same two triangles, we can decide if these two figures are similar by finding out if they're proportional. So if they're similar, their sides have to be proportional. We can use something that we learned about in proportions in order to figure out if these are similar or not by comparing two sets of ratios and seeing if they can simplify to the same number. Okay? So we have to use corresponding sides. So let's say we take 4 and 3 from this triangle, and then the corresponding sides are 2 and 1.5 from this triangle. Okay? Now, I have the same corresponding sides on top, 4 and 2, and corresponding sides on the bottom, 3 and 1.5. Now, one method that we learned to find out if this is proportional is cross-multiplying. So 3 times 2 is 6, and 4 times 1.5, when we figure that out, is 6.0, and that's the same as 6. So yes, these sides are corresponding. If we need to, we can also take another set of corresponding sides to make sure that these last two sides are corresponding. In a triangle, they should be if the angles are the same. So let's try 6 and 3, and then 3 and 1.5. So now we have 3 times 3 is 9, and 1.5 times 6 is 9.0. So now we have proven that all the sides on these two triangles are proportional, so these two triangles are similar. Okay. Now, we need to find out which trapezoid is similar to the trapezoid named DEFG. I'm going to use the same method to figure out which one of these is similar. So it gives me two sides here, 4 and 12. So I'm going to start with that, 4 over 12. Now, I have to use the numbers in the other trapezoids in the exact same order. I went short side, long side for my first ratio. So I have to do short side, long side for my second ratio. They have to be corresponding. 4 and 6 correspond, 12 and 14 correspond. When I cross multiply here, I get 72, and over here I get 56. So these are not similar trapezoids because their sides are not proportional. Okay, so this is not a proportional trapezoid. Let's try the next one. 4 and 12, and 3 and 9. If I wanted to, I could simplify these down first before I multiplied. I'm going to get 36 for 4 times 9, and 36 for 12 times 3. So these two numbers match. That means these are proportional. These ratios are proportional. That means these two trapezoids are similar. The other thing you may have noticed is that if I had just simplified my fractions with 4 over 12 and 3 over 9, they both simplify to 1/3. So we can tell already that they're proportional. All right. We can use these kinds of proportions to figure out how tall something is. If we know the height and the shadow of one item and the shadow of a second item, we can find its height. So when we're looking at this, we've got a tree. We don't know how tall it is. And its shadow length is 63 feet. Then we have a geyser that we know shoots 60 feet into the air, and its shadow is 42 feet. Now, of course, these measurements need to be taken at the same time of day so that the shadow lengths will be proportional as well. We're going to set up our first set of ratios on this proportion with 60 and 42, height over shadow. So I'm actually just going to call it tall and shadow. I'm going to put my labels out so I know where to put my numbers. So the geyser is 60 feet tall and has a shadow of 42 feet. The tree, we don't know how tall that is. That'll be X. And it has a shadow of 63 feet. So to figure this out, I'm going to take 63 times 60. And I'm going to divide that by 42. So remember, you multiply across and then divide by the number that's left. Number 1 is multiplying, number 2 is dividing. So 3,780 divided by 42. I'm going to try 9 here. So that's 18, 37. That comes out perfectly. Now, just because I have subtraction and I get 0 doesn't mean I'm done and this answer is 9. I still have a 0 in my dividend. So I need to put a 0 above that to hold that place. So the answer is 90 feet. It wouldn't make sense to have a tree that's 9 feet tall with a shadow of 63 feet long, especially when we know that the height of the geyser is more than its shadow. So the height of the tree has to be more than its shadow as well. Okay. In our next example, number 3, Destiny wants to resize a 4-inch wide by 5-inch long photograph for the school newspaper. It is to fit in a space that is 2 inches wide. How tall, or what will the length be of this photograph? Okay, 4 inches wide, 5 inches long. So I'm going to put wide over long. Okay, my first photograph is 4 inches wide over 5 inches long. My second photograph is 2 inches wide, and we don't know how long that's going to be. Now we have our proportion set up. We're going to multiply across. 5 times 2 is 10. 10 divided by 4 is actually 2.5. So 2.5 inches. The other way to solve this, other than multiplying across and dividing, you could say 4 divided by 2 is 2, and 5 divided by 2 is 2.5. So 2.5 inches long for that photograph. In number 4 and 5, we are given 2 similar figures. It tells us right here that they're similar. That means they have to be proportional. And we can use a proportion to solve for x. In this case, we're looking for this little x right here. So we're going to take the figure where we know 2 of the dimensions, the short side and the medium side. So I'm going to take 4 over 7. I'm going to go short over long, 4 over 7. So over here I also have to do short over long, and that's 20 over x. Okay? When I multiply across, I get 140. And then I can divide by 4. Or I can say 4 times 5 is 20. So 7 times 5 is 35. So to correctly answer this, x equals 35. For number 5, same situation. We've got corresponding sides. We have the measurements for 3 of them, but we're missing 1. So on our small trapezoid, or it's quadrilateral probably, on our small quadrilateral, we're doing 15 over 13. Okay? Corresponding side to 15 is x, so that'll go on top in the other ratio. The corresponding side to 13 is 39. So now, 13 times 3 is 39, and 15 times 3 is 45. Okay? We could also have multiplied across and divided by 13. Finally, example number 6, we once again have the tree and shadow, and then now we have a person and their shadow. So if a person is 6 feet tall and casts a shadow of 5 feet, how tall is a tree that casts a shadow of 40 feet? I'm going to use my 2 corresponding sides. I'm going to put 6 over 5 for height over width. 6 over 5. And then 6 corresponds to x. That'll go on top. 5 corresponds to 40. I know that 5 times 8 is 40, and 6 times 8 is 48. So this tree is 48 feet